Hey there, welcome to Lab Partner 101, your study buddy for making science and math simple. I'll walk you through tough concepts step by step so you never feel lost. Let's dive in. Carbon. It's in the air, in the ocean, in every living cell. It flows through plants, animals, rocks, and the sky in one of Earth's most vital systems, the carbon cycle. This cycle controls the planet's thermostat, and when it's disrupted, the effects ripple through climate, ecosystems, and even extinction events. Today we'll explore how carbon naturally moves through Earth, how human activity has reshaped that flow, and how we know carbon imbalances have changed the planet before. If you're into science made visual and clear, feel free to subscribe for more breakdowns like this one. The carbon cycle is the natural movement of carbon atoms between Earth's major systems: the atmosphere, oceans, living things, and solid Earth. Imagine carbon like a traveler. It enters a plant through photosynthesis, gets eaten by a rabbit, breathed out as CO2, and then absorbed by the ocean or locked into a rock. It's always moving, changing forms, switching systems. Most carbon moves in and out of living things relatively quickly, on the order of days to centuries. But some carbon gets buried in the deep earth and locked away for millions of years, as in limestone, coal, or oil. The key idea: Earth's climate depends on how much carbon stays in the atmosphere versus how much is stored elsewhere. The carbon cycle is the balancing act that keeps that system stable, until something tips the scale. Let's break the carbon cycle into its major components. Atmosphere. Carbon here exists mainly as carbon dioxide, CO2, and methane, CH4. These gases trap heat and regulate global temperature. CO2 enters the atmosphere through respiration, combustion, and volcanic eruptions. It leaves when absorbed by plants or dissolved into the ocean. Biosphere. Plants take in CO2 during photosynthesis and use it to build sugars. Animals eat the plants, use the carbon for energy, and release it again through respiration. When organisms die, decomposers break them down, sending carbon back into the soil and atmosphere. Lithosphere. Earth's crust and upper mantle. Some carbon gets buried as dead organisms pile up on the ocean floor. Over millions of years, pressure and heat transform that carbon into sedimentary rock or fossil fuels. This part of the cycle is very slow and acts like a long-term carbon vault. Oceans. The ocean is Earth's largest active carbon sink. It absorbs CO2 from the air, where it reacts with water to form carbonic acid. Marine organisms use dissolved carbon to build shells and skeletons. When they die, some of that carbon sinks to the ocean floor. Together, these systems form a dynamic network of carbon exchanges, some fast, some slow. The planet's temperature depends on keeping these flows in balance. For most of Earth's history, the carbon cycle was driven by slow, natural processes: weathering of rocks, plant growth, volcanic eruptions. But in the last few centuries, specifically since the Industrial Revolution, humans have added a new force to the equation. By burning fossil fuels, coal, oil, and natural gas, we've unlocked vast amounts of carbon that had been buried for millions of years. That carbon goes straight into the atmosphere as CO2. We've also disrupted the biosphere. Deforestation removes trees that would otherwise absorb CO2. When forests are cleared and burned, the stored carbon is released, adding even more to the air. And although oceans continue to absorb CO2, there's a limit. As they do, the water becomes more acidic, harming marine life and reducing the ocean's capacity to act as a carbon sink. In short, human activity has overloaded the fast parts of the carbon cycle with carbon from the slow part. That imbalance is pushing Earth's climate into uncharted territory. Carbon dioxide is a greenhouse gas. It traps heat in Earth's atmosphere. That's not a bad thing in itself. Without CO2, Earth would be a frozen planet. But small increases in CO2 lead to measurable warming. Since 1850, atmospheric CO2 has risen from about 280 parts per million to over 420 ppm. That may not sound like much, but climate operates on razor-thin margins. More CO2 means more trapped heat. That causes glaciers to melt, sea levels to rise, and weather patterns to shift. The link between carbon and climate isn't theoretical, it's been observed. Satellite data, ocean temperature records, and thousands of surface sensors all show a planet warming in lockstep with rising CO2. And the fingerprint of human activity is clear. The carbon in fossil fuels has a distinct isotope ratio. When we burn them, the atmospheric signal changes in a way that matches our emissions. Carbon naturally exists in several isotopes. versions of the same element with different atomic weights. The two most common are carbon-12 and carbon-13. Carbon-12 has 6 protons and 6 neutrons, while carbon-13 has an extra neutron. Plants, through photosynthesis, preferentially absorb carbon-12. It's slightly lighter and more reactive. Over millions of years, this plant-based carbon becomes buried and transformed into fossil fuels. So coal, oil, and natural gas are all strongly enriched in carbon-12. When we burn these fuels, we release that ancient carbon-12 back into the atmosphere, and scientists can detect the shift. By measuring the ratio of carbon-13 to carbon-12 in atmospheric CO2 over time, we see a clear decline in the relative abundance of carbon-13. This means more and more of the carbon in the air is coming from fossil sources, not from volcanoes or natural respiration, which don't change the isotope ratio the same way. This declining ratio, combined with rising total CO2 levels, gives us two lines of evidence. Not only is carbon increasing, but it's specifically fossil carbon, a chemical fingerprint that ties the rise directly to human emissions. It's one of the clearest pieces of physical evidence that climate change isn't just happening, we're driving it. This isn't the first time Earth has seen carbon-driven climate shifts. The geological record shows several moments when a spike in CO2 triggered major upheaval. One example, the End-Permian extinction about 252 million years ago. Often called the Great Dying, it wiped out over 90% of marine species and 70% of land species. One leading theory is massive volcanic eruptions released huge volumes of CO2, leading to global warming and ocean acidification. Another example, the Paleocene-Eocene thermal maximum, around 56 million years ago. During this event, global temperatures soared by at least 5 degrees Celsius in a geologically short span. Carbon isotopes from sediment cores suggest a sudden release of carbon, possibly from methane hydrates or volcanic activity. These ancient events matter because they show us how sensitive Earth's systems are to carbon imbalances. They also give us clues about what could happen if current trends continue unchecked. Climate change doesn't just make the planet warmer, it sets off feedback loops that amplify and accelerate the damage. When ice melts, it exposes darker land and ocean beneath, which absorb more sunlight and heat. That leads to even faster melting. As permafrost thaws, it releases methane, a greenhouse gas that's more than 25 times as potent as carbon dioxide at trapping heat over a 100-year span. That surge of extra warming pushes the system even further. Warmer oceans can't absorb as much CO2, which leaves more carbon in the air. The absorbed carbon also turns seawater more acidic, damaging coral reefs, weakening marine food webs, and threatening ocean life at scale. And the effects are now reaching across ecosystems. Forests once stored carbon, now they burn. Species that can't adapt fast enough are disappearing. We're currently in what many scientists call Earth's sixth mass extinction, with species vanishing at rates hundreds to thousands of times higher than normal. Ecosystems are unraveling, and once a key species collapses, the domino effect can be impossible to reverse. Entire habitats can disappear, taking biodiversity, carbon storage, and human livelihoods with them. The harsh truth is this: climate change is already here, and we can't fully undo the damage we've done. The carbon in the air today will shape the climate for generations. But that doesn't mean we're out of moves. We can still act, decisively and immediately, to slow it down. We can stop making it worse. We can stabilize what's left. We can protect forests, restore wetlands, shift away from fossil fuels, and invest in clean energy and carbon capture. If we scale up fast, we can still avoid the worst-case scenarios, the truly catastrophic levels of warming, displacement, and collapse. Because the longer we wait, the narrower the path becomes. The clock is ticking, but there's still a road ahead worth fighting for. Understanding the carbon cycle isn't just academic, it's the key to managing the future of life on Earth, including our own. If this helped you understand Earth's carbon story a little better, hit like or drop a question in the comments. I'd love to hear what you're curious about next. In our next episode, we'll explore how scientists study ancient climates, using ice cores, tree rings, and sediments to reconstruct Earth's history. The carbon cycle is Earth's way of balancing energy, life, and time. When it runs smoothly, the planet thrives. But when the balance breaks, history shows the consequences can be massive. We're not separate from that cycle, we're shaping it. And the next chapter is still being written,